There you go.
Hi everyone. Thanks for coming out tonight. My name is Professor Matthew Szydagis. I'm a assistant professor of physics at the University of Albany, and I'm going to be telling you tonight about dark matter. But before I launch into dark matter, I wanted to tell you and all about our invisible universe. I first wanted to start out with a little bit about Isaac Asimov, since tonight's talk is hopefully part of an ongoing effort aimed at the sort of the resurrection of Isaac Asimov's famous Institute on Man and Science here in Rensselaerville, discussing connections between humanity and science. So a personal story of mine that's kind of connected to Asimov, not directly, but I was inspired to go into science by science fiction, and I always wanted to be Lieutenant Commander Data for Star Trek Next Generation, even though he's an android, obviously I'm not. So I'm too young for Spock. I caught up on the original Star Trek later, since it was already off the air, not even in reruns. When I had been a child. So Data's positronic brain was inspired actually as an homage to Isaac Asimov's robot artificial intelligence series. So here are some of my favorite books. Actually, there's the Isaac Asimov's robot series, Caves of Steel. That's a great book from 1954, and it still reads very fresh. And then a childhood favorite of mine on the left, The Unidentified Flying Objects. It's not by Isaac Asimov, it's Isaac Asimov's Library of the Universe, talking about the possibilities of extraterrestrial life and travel. So these were very formative and inspirational for me. So I was really inspired by things like this from a young age, in order to later then go on to become a scientist. So now the story of dark matter, this cutting edge scientific inquiry. But I want to begin the story of dark matter. Let me see, I can move out now. Oh, yeah, I've got my clicker. Okay, so the historical perspective starts with these two individuals. There's Fritz Zwicky and there's Vera Rubin. So there are some who say that Zwicky was first, or that Vera Rubin was first, in terms of who gets the most credit for the similar work in dark matter. So Fritz Zwicky in the 1920s looked at galaxies, a cluster of galaxies called the Coma cluster, and found that the velocities of these galaxies were so large that the cluster should break apart. It should not be gravitationally bound. That was ignored, though, for many decades, and he had very large uncertainties in his analysis. But then in the 1970s, we have the work of Professor Vera Rubin. And Rubin's work was really transformational. And she, unlike Zwicky, looked not at galaxies, but at stars within galaxies, and found that stars within galaxies were revolving around the centers of galaxies faster than they should. And so both of their work pointed towards there being additional matter, additional mass generating a gravitational field beyond the matter we see visible in stars inside of galaxies. So this is a great example of Professor Rubin's very important work, where she discovered that if you look at any galaxy, instead of the speeds of rotation of things going on in centers of galaxies, instead of going down, instead speeds seem to be going up, flattening, or they keep increasing. And this is not what we expected. If we look at our own solar system, planets or objects like Neptune and Pluto are, of course, orbiting much more slowly, have a longer year than things closer in, like Mercury and Venus, and then the inner planets. And so we expect the same behavior on large galactic scales, and we don't observe it. So this is not exactly the same behavior, since here, moving further away from the sun, here we're talking about a galaxy that's an extended mass. And so there's first an increase here you do expect until you're past most of the mass here at distance. But eventually we would expect it to start seeing a drop off, just like we do gravitationally on smaller scales in our own solar system. Now we can explain pictures like this by postulating the existence of additional matter. And in a galaxy like our own, so here's a cartoon diagram of the Milky Way. Here's the sun 26,000 light years away from the center. There's a galactic center where the supermassive black hole is at the center of our galaxy, as in the center of most or all galaxies. This is central bulge of stars orbiting the central black hole. And this is the plane of the galactic disk, which is over 100,000 light years across this way, but it's very thin this way. But we have these red dots here. These are globular clusters. They're dense clusters of stars that are outside of the plane of the galaxy but still seem to be trapped gravitationally and are orbiting. And we can't seem to explain this without postulating extra invisible mass in sort of a spherical or elliptical halo of dark matter represented by this gray haze here. That's additional matter. And another way of, so this is a cartoon, but another way of looking at this with real data is, so these are images from the Chandra X-ray Observatory. And this is galaxy NGC 0507. So these fuzzy patches here are not stars. These are galaxies with hundreds of billions of stars each, just to give you the scale here. And so this is a galaxy with other satellite galaxies around it. This is the visible light. But if we look with X-rays, we see that we have X-ray emitting gases that are in the interstellar or intergalactic medium here, and there doesn't seem to be anything gravitationally binding them into this cluster of galaxies here, but yet there's gas all around. So speaking of gravity though, another way we can look at this is through an effect called gravitational lensing. So a strong enough gravitational force actually bends light, and the amount of bending allows you to calculate the amount of mass, or the amount of matter that's doing the bending. So what you're looking at here is actually these little curvy things here are not different galaxies, but you're looking at the same galaxy whose image is being repeated and distorted. So gravity can act like a lens, just like eyeglasses or contact lenses. You can bend light. It's a different principle than we have in optics. As I said, you have a warping of space-time from gravity that distorts light. But that distortion of light allows you to calculate how much matter is doing the distortion. And what we find from this is that this agrees with the galactic rotation study you just saw. There is more matter than is visible in the stars and galaxies here. So the next piece of evidence that there's extra invisible mass in the universe that we don't see, this is called the bullet cluster. This is actually a collision between two galaxy clusters over 1 billion light years away. And what you're looking at here are three images superimposed on each other. You have the visible light image, you have the gravitational lensing map in blue, and then you have the X-ray emitting gases in pink. And this is just another way of looking at it, the contours here representing the gravitational distortion calculated on this image in blue. And what we find is that we have two clusters of galaxies colliding and gas from the collision mixing in the center, but the centers of mass, as defined by the gravitational lensing studies in blue, do not match the centers of mass in the pink here or in the visible optical center of mass. So again, most of these spots, with some of these are stars like here, but most of the splotches of light in this image is we're looking at galaxies with hundreds of billions of stars. So these are two clusters of galaxies that are colliding and merging. And the only way we've been able to mathematically and robustly explain this image is that we have matter that's not visible, not shining in the stars inside these galaxies, that kind of slips out of the collision point and forms these two lobes on the side. So up until the bullet cluster, and even through the bullet cluster discovery around 2006, I believe it was, there's still another option, which is that our understanding of gravity is wrong. There is no extra matter. We can modify the law of gravity. So here's a joke from XKCD, from Randall Patrick Monroe. Former Master of Physics motto: yes, everybody has already had the idea, maybe there is no dark matter, gravity just works differently on large scales. It sounds good, but it doesn't really fit the data. So there are many, like theoretical physicist Eric Berlin. So this is not a crackpot idea, it's a very serious idea that dark matter is not real, and that we don't need to postulate additional matter. We just don't understand gravity. Now, the issue with this is we think we understand gravity very well. We have recently had the Nobel Prize-winning discovery of gravitational waves, which was yet another confirmation of Einstein's theory of general relativity. So we think we understand gravity fairly well, not just on the scales of our solar system, but beyond it. And so while it's still possible to come up with modified theories of gravity that explain some of the data, maybe even more than half, it's very hard to come up with an idea of modified gravity that fits all of the data. So the more data we collect, the more evidence we find that there is more to the universe than what we can see. So beyond just the rotation curves and gravitational lensing, we also have something called the cosmic microwave background radiation. So this is a microwave scale radiation that comes from all parts of the sky and is sort of, you can think of as the leftover a radiation from the Big Bang. So when this was discovered in the 1960s, it really made the Big Bang theory take off against the opposing model, which was called steady state, that the universe is eternal, it doesn't have a beginning. The discovery of the CMB, as it's called, is pretty strong evidence that the universe does have a beginning. And by studying the very small, very small, very much smaller than 1% temperature fluctuations in the CMB. That's what these orange and blue here pixels represent hot and cold spots, where basically outer space and stuff is very slightly different temperatures. We can match these slight variations to computer models, and these very slight variations tell us many things. Tell us the age of the universe, the shape of the universe, the size of the universe. It's all the very an entire talk can be devoted to the CMB. It's its own large, intense field of research, but it's not my field of research. So why I'm bringing up the CMB is that if we mathematically analyze the fluctuations in the CMB, it allows us to come up with this pie chart, because different forms of matter or energy will affect the CMB in different ways. And so this pie chart is known as the standard cosmological model, or the lambda CDM, or cold dark matter model. And so this pie chart shows the multiple components that compose our universe today, as the fractions can evolve over time. So what we have in this pie chart, 69% is this thing here called dark energy. There's absolutely nothing to do with dark matter. Well, it could, most likely not, except for sharing the term dark, because we don't know what the heck it is. So dark energy is something we don't understand that's causing the expansion of the universe to go faster. So it's not causing the expansion of the universe originating from the Big Bang, but it's accelerating, it's increasing the rate of expansion of the universe. We don't know what it is. It does seem to have sort of a kind of an anti-gravitational-like effect. It's pushing things apart. And so we know even less about this than my topic tonight, dark matter. So dark matter, according to the CMB and all the other studies I've shown you so far, seems to make up about a quarter, 25% of the universe. And then here we have atomic matter at 5%. Now you might think, oh, we're only made up, the stuff that makes us up in this room and make up our bodies is only 5% of the universe. No, actually, it's much worse than that. So of this 5%, 75% is hydrogen, and 25% is helium. So again, 75% is hydrogen, 25% of that chunk is helium. So that rounds to 100%. So most of the atomic matter, ordinary matter in the universe, is either hydrogen or helium. Everything else, oxygen, silicon, carbon, phosphorus, all these elements in the periodic table and elements of life, we are the sub 1% dregs of the universe, the smallest quantities. Too small to appear on a chart like this. There are other things we can put, neutrinos, photons, black holes. I'm always asked, are black holes dark matter? Well, there don't seem to be enough of them. Of course, this could be wrong, and we keep going back and forth over the years about, wait a second, what if, but we just, the current consensus is that there's not enough black holes to make up the 25% dark matter. So, I'm always thinking, given how small ordinary matter I think we understand is, I always wonder, are there aliens out there made of dark matter? And there's a brilliant dark matter alien scientist who goes to his government and says, I need money to look for the missing 5% of the universe. And they're like, you're crazy, 5%, that's not real. It's just an error, there's no atomic matter. And the scientist says, no, I've got it. I know what the missing matter is. I'm going to call it the proton. And we laugh, right, because there's neutrons, electrons, everything else, but if 75% of this is protons, actually that individual would not be far off from the truth, because the vast majority of atomic matter is just protons. This is just a hydrogen gas. So this is the state of affairs, and this pie chart we've managed to cross-check multiple different ways with different astronomical studies, and we always come to the same answer. And our earlier studies going back 50 years or more even concur with this. So before we knew about dark energy, you'll see numbers quoted like 85 or 90% of the universe is dark matter. And that's because 25% divided by 25 plus 5 is about 85 to 90%. So before we learned about dark energy, you'll see quotes from older studies or articles from the 1980s and 90s, and they're not contradictory. It's actually consistent because this chunk was missing. And so all our previous work, like the gravitational lensing and galactic rotation curves, agree with this study, with this picture we get from the CMB. So now, let's look at the large-scale structure of that atomic matter, or visible matter in the universe, and what we find is that it clumps, and the galaxies tend to cluster in little pockets. And the way we've been able to explain this, and we can now fairly well with computer simulations, is that we have here what happens over time as the universe evolves, is that dark matter clumps gravitationally. And ordinary matter in the form mostly of hydrogen and helium gas is attracted to the dark matter clumps. And then what do we get? We get the structure of galaxies and galaxy clusters that we observe out in the universe. And whenever I look at, so these are computer simulations, but this is real data. So when we look out in space, and we've mapped, billions upon billions of galaxies, we see what is called the cosmic web. So dark matter causes matter to clump, whereas dark energy in the expanding universe pushes things apart. And so we have separate clumps of galaxies, of clusters of galaxies, and clusters upon clusters, superclusters. But then we also have these great voids with very little matter in them. Whenever I see images like this, though, I can't help but notice it seems a lot like neurons in a human brain, or mammalian brains, or almost any brain, or any vertebrate brain for that matter. So this could just be a grand coincidence, or this great cosmic joke. But if you do look at the structure of the universe, it does look like a giant brain. But I told you about all this astronomical evidence we have for additional matter, but what is it? What is that stuff? So we have a couple different ideas. We have many, much more than a couple different ideas. I don't have time to go into all of them. But on the next slide, I'm giving you two great examples. So one idea is called supersymmetry. So this is the idea that for every particle that has one type of spin, there's another called a superpartner or sparticle that has a different kind of spin. And these partners, represented in this cartoon with larger radius circles, this doesn't represent physical size. It's saying that the superpartners have more mass. And the lightest of these new particles might have the right properties to explain dark matter. So this is not a dark matter theory. Supersymmetry of theory is just stands on its own as something in particle physics. It's convenient though. You could kill two birds with one stone. If supersymmetry is real, that's nice on its own. But it might also, as a secondary effect, if supersymmetry is discovered, we may have a good candidate. One of these heavier new particles could be dark matter. Now, this is kind of analogous. It's not a perfect analogy, but this is kind of like matter and antimatter. So the big difference between supersymmetry and antimatter is that antimatter is real. I mean, we've been using it since it was discovered in the 1930s. So you can't make enough of it though to make a weapon like in Dan Brown's Angels and Demons. It's crazy because we make individual particles of it, very small amounts. But antimatter is a similar idea except with electric charge. So for every particle, there's an antiparticle that has equal but opposite electric charge. This is something similar, but with spin. It doesn't mean opposite spin. It's a little more complicated than that. But this is, again, a similar idea in the sense of symmetry, that we see certain types of particles with certain numbers, with certain values, and we postulate what if there are others that have a complementary different value. So there are sort of these mirror particles then that maybe could explain dark matter. This is a very popular notion. There's another one, maybe not as popular, and this is the idea that there are extra dimensions. So what I mean by that is imagine if, so there's another direction to move other than left, right, up, down, in, out, the F3, X, where the X, Y, Z coordinates we know and love. Imagine there's a fourth direction to move we can't perceive. And I don't mean time. So if we're counting time as the fourth dimension, then this would be a fifth or higher one. The problem is there's no analogy, there's nothing I can do to explain it. If we all lived on this carpet, let's say we all lived in flatland, there would be no way to explain to the residents of flatland what up and down mean. There's no vocabulary for it. So similarly, what if there's another direction we can't perceive? But now, let's take that a little bit further because we need to explain why don't we perceive that direction? And it could be that it's very small and curled up. It's not just linearly infinite like there are three coordinates directions we have now. So let me explain what I mean by that. Imagine you're looking at a garden hose from very far away. You might think it's one-dimensional, it's just a line. But if you look closer, you see the line has thickness. It's two-dimensional. But if you look even closer, you see, no, it's a two-dimensional surface wrapped in the third dimension, and it's actually a cylinder. It's a cylindrical surface. So it's a plane that's been wrapped up. So similarly, it could be that we don't perceive extra dimensions because they're very small, and they're curled up or curved in some way on very small length scales, subatomic scales. But if we have this sort of cylindrical geometry to our additional dimensions, this would have a consequence in particle physics that we get extra particles. And that's called the Kaluza-Klein tower. And the Kaluza-Klein tower, just like supersymmetry, gets you extra particles. So maybe one of those particles, maybe the lightest one, if it's stable, if it doesn't decay, maybe that explains dark matter. We get a natural extra particle. These are just two examples, though, out of dozens. So here's a great cartoon, again from XKCD, showing dark matter candidates at a very great range of masses. And about half of these are real, but there's a lot of jokes hiding in here. I love electrons painted with space camouflage, no-see-ums, 8 balls, obelisks, monoliths, pyramids, space cows, I love this, black holes ruled out by buzzkill astronomers. Dang astronomers, always ruling things out. So, and here's another great one. Maybe those orbit lines in space diagrams are real and very heavy. Those dashed lines are like the orbit of the Earth. So, but some of the crazy ones, cue balls, that's a real thing. Sterile neutrinos, that's also real. A lot of these crazy names are actual real models or hypotheses. But there's a very broad range here. Dark matter could be the size of a supermassive black hole or so small that it has nearly zero mass. It could be anywhere in between. We don't know because we don't know what it is. And so there's no shortage of ideas. I've just given you on the last slide here, this slide, two very broad possibilities, categories. Both of these, though, kind of lead to the same thing. They lead to a particle that's could be a few tens or a few hundred times heavier than a proton. But going back to the idea of extra dimensions, there's another idea. This is called the Rensselaerville model, that dark matter is just ordinary matter, but it's hiding in a direction we can't see. It's in another dimension, an extra dimension. Now, I should be clear. I don't mean dimension the way it's used in science fiction. It doesn't mean like a parallel universe. It's our universe still. It's just another direction to move that we're capable of perceiving. Now, what's really elegant about this approach is that you don't need any new particles. Oh, dark matter, it's just ordinary matter, but it's just it's on another plane of existence in a sense. It's in another direction. So if we imagine our universe as a flat surface, using our flatland analogy again, dark matter is, up or down. It's a direction we do not perceive. What's nice about this is it gives a natural explanation for why gravity is so weak. So you might wonder, gravity is weak, but is it really hard to leave the Earth's surface? Well, the Earth is really big, and the sun and things like that. It's kind of a bit of a mystery in physics that why is it I can take a refrigerator magnet and a paperclip. That refrigerator magnet wins. It beats the entire planet Earth. Why? Why is electromagnetism so strong? So the Rensselaerville model explains that by saying, gravity appears to be very weak in our dimension because it's leaking. Gravity leaks across all dimensions. It's a nice idea, however, if this is true, then I'm wasting my time in my experiments, which is trying to find dark matter here in our dimension as a new particle. So if dark matter is here in our plane of existence, what could it be? So we went through all these ideas with supersymmetry. Supersymmetry and models like that give us something called a WIMP. That's an acronym that stands for Weakly Interacting Massive Particle. And here's a nice plush toy you can buy for your kids from the Particle Zoo, particlezoo.net, and this one's dark matter. I know that the plush toys, they're different masses for representing the mass of the particle they are. But since we don't know what the mass of one dark matter particle is, I don't know how massive they made it. So, also, I hope they use the logarithmic scale because there are particles that differ by many millions. So, but this is the plush dark matter toy. So, dark matter may not be a new fundamental particle. I would bet that a substantial fraction of you right now are thinking, why can't dark matter just be ordinary matter that happens to be dark? And that's an excellent question. So one idea we had was that dark matter actually made something called machos. And you can see we love our little jokes in physics, right? Macho versus WIMP. So macho stands for massive compact halo object. This is the idea that dark matter is made up of a lot of ordinary matter in dark configurations. For instance, rogue planets that have been ejected from their star systems, and so they're dark. There's no star. They don't have a primary star, a sun that light is bouncing off of them anymore. Or they're dead stars, or brown dwarfs as they're called, like this artist's illustration here. This may look a lot like Jupiter to you. So the idea here is you have Jupiter-sized or larger, or even 10 or 100 times larger than Jupiter-sized objects. And these objects don't shine unless they're reflecting light of a star. They don't shine because they weren't large enough to become stars. and ignite nuclear fusion. So you might think, what if galaxies are populated with a bunch of these brown dwarfs, rogue planets, dead stars, black holes? This doesn't work though, because first, we don't seem to have enough of them when we look for this and extrapolate from small studies to then extrapolate and estimate how much we have in entire galaxies. But there's another reason, which is that ordinary matter interacts many different ways, not just gravitationally, electromagnetically, all these different things. And our studies like that of the cosmic microwave background, the CMB, tell us that whatever dark matter is, it interacts primarily through gravity. So that kind of rules out almost a lot of our standard model particles. And so that's why, so for the rest of my talk, I'm going to be focusing on this cute guy here on the left. So let's imagine that dark matter is made up of some sort of heavy fundamental particle that's not like quarks or protons that make up you and me, that has some different properties, including being heavier. And I should stress that WIMP, weakly interacting massive particle, that actually is generic. So that could be supersymmetry, could be collision Klein, extra dimensions. It's just an umbrella term for sort of a vanilla, generic dark matter candidate. So if these particles are around, though, as we rotate and as we revolve around the sun, and as the sun revolves around the center of the galaxy, we should be able to see a variation in the signal that we get if we try to detect this dark matter. And this is called the WIMP-WIMP. If there's dark matter particles that are at rest in the frame of reference of the galaxy, and the sun is racing through the galaxy or around the center of the galaxy, then we should see variation in the amount of WIMPs we get over the course of a day or over the course of a year. But so you can look for this daily or annual modulation, but that does not tell you yet. I haven't told you, well, but what kind of technology can we use if dark matter is a particle, say it's a WIMP, it's a new kind of particle we haven't seen before. How do we find it? How do we discover it? And so there are three main detection strategies. One is called direct production. This is where you bang standard model particles together like protons at the Large Hadron Collider at Switzerland in Europe. And you try to make new particles. Another approach is called indirect observation. This is where you wait for dark matter to interact with itself. You have to assume it interacts in some way other than gravitational. And then you can bang dark matter together. So reading the diagram this way, you can bang dark matter together, something happens that we don't understand. And we produce things like gamma rays or neutrinos, particles that we already know and love and can detect. So that's indirect observation. That's usually done with satellites, with spacecraft. There's also experiments in South Pole, like IceCube. And then so we have direct production, we have indirect observation. But there's a third method called direct detection. And that is the focus of my work, of my research. And with direct detection, what you have is dark matter bumping into a standard model particle. So it like bumps into an atom in your detector, and what you see is the energy of the interaction after the dark matter has collided with an atom in your experiment. So that is called direct detection. And the idea behind direct detection is that you literally have a billiard ball-like collision. You have your dark matter comes in and knocks into something, but then it causes something else that then you can measure and detect. So in this canonical WIMP model, WIMPs are more likely to interact with the nucleus, but then you have to be careful not to trigger on things that interact with the electrons around the nucleus. You can have naturally occurring radiation like gamma rays that are going to interact with the electrons on the outside. And so this is not an easy task because you want to discover dark matter but not have a false positive where you just, you've rediscovered something ordinary that we already know about. And so this is a very broad problem, the problem of background noise. So one common issue in dark matter experiments is radon. So I love this. I grabbed this little guy, radon, the silent killer. So that's not to downplay the danger of in your basement as a radioactive gas, but it's an even more serious problem for an experiment trying to detect dark matter, because you don't want to be just detecting radon all the time. And so radon is naturally occurring in the atmosphere. Well, I don't know if natural is the right word, it would probably contribute to nuclear testing, but over decades, but it's a serious problem because it's just everywhere in very small amounts. And so that gets into your dark matter experiment, and radon produces gammas, it produces alpha particles, what they're called, and so this is a serious issue. So you need to be able to have a very, very pure detector, all your solid materials and your fluids that go into your experiment. Another problem is a neutron. So a neutron, as far as we know, which is that particle you learned is one of those in the nucleus, right? You have protons, you have neutrons. Neutrons are naturally occurring, can knock into nuclei and look exactly like dark matter. This is actually not as big of a problem as radon. With neutrons, the thing about neutrons is that even though they could look like a dark matter interaction, they will also scatter multiple times in your detector. So if dark matter only interact so rarely, it's only going to scatter once, but a neutron can scatter multiple times. So that's how you can tell the difference. But there is a benefit to neutrons just having this billiard ball-like collision, is that neutrons are the gold standard in calibrating our experiments. That's how we know our experiments work. We test them before deploying them by shooting neutrons at them. There are other problems like gamma rays that are naturally occurring from radioactive elements like uranium and thorium that are all around us, that are inside of everything. So we often talk about how we need to build our dark matter experiments from low radiation materials. And that always scares people. Low radiation, your materials are radioactive? When we say low radiation, we mean that when we construct a dark matter experiment, it needs to be less radioactive than you or me, or a banana. Okay, so when I say low radioactivity, I mean depending on the type of dark matter experiment, you could ruin it. You touched it without a glove because you have radioactive potassium in your sweat. It's completely harmless. Small amounts naturally occurring, it doesn't bother you. So there is no such thing as zero radiation that doesn't exist. Okay, that may exist legally. It's wrong. There's no such thing. We are all radioactive to a large amount compared to dark matter experiments. So if you want to discover a new particle, you can't have normal radiation that we already know about. You can't have that flying around. And so a banana, which has a lot of potassium, is significantly more radioactive than most of the parts, the metals and plastics that go into building our dark matter detectors. But that's not good enough. You can build something out of low radiation, concrete, plastic, metal, things like that, but you've still got naturally occurring cosmic radiation from the sun, from distant galaxies, supernovas. We're constantly bombarded by what are known as cosmic rays. So in fact, people are always worried about radiation and worried about like the scanner at the airport. I'm pretty sure you get more radiation depending on your flight path and how high you are. It's possible to get a significant dose of radiation, but it's not going to do anything to you from a flight, from a plane, because you're higher up off the ground, so you have less shielding in the atmosphere. This is not, as I said, this is not significantly harmful to humans. It's not significantly harmful, but it is harmful to a dark matter experiment because you're trying to discover a new particle, but you're constantly bombarded by all these naturally occurring cosmic particles. So for this, even the surface of the ground is not good enough. So for direct detection experiments, we not only build them out of very high purity, low radioactivity material, that takes care of the left half here, that's not good enough. We also need to go deep underground. So on the experiment that I work on, that I'll be showing you, I worked on the Lux experiment, now its successor LZ. We work in a former gold mine in South Dakota that's nearly a mile underground. And even that's not the best. That is not the deepest underground dark matter experiment. So we got to get deep underground so that the rock helps block out the naturally occurring radiation. But what is it that we put underground? What's the technology we use? So the different technologies we use can sort of be put into a few different broad umbrella categories. And the first one is light. So some materials, you may be familiar with this from childhood. If you have kids, you have materials that naturally phosphoresce, for example, decorate your kids' room with glowing stars. So there are materials that produce light. When light or something else, some other particle or radiation hits it. So this is called in science scintillation. So light from de-excitation of atoms and different materials leads to what's called scintillation light. It's like, the same having a scintillating personality, except it has a lot more precise meaning in science. So your detector has a scintillating personality, it means something else. But you can also rip electrons off of atoms. That's called ionization. So scintillation comes from electrons that just get excited. They're not excited as in, they're happy to see you or happy to see the dark matter. That means they move up to a higher energy level. But when they come back down, they release light. But electrons, instead of just moving to a higher energy level but still bound inside of an atom, can be completely removed from an atom. And that is called ionization. Another method is looking for phonons. This is not photon, this is phonon. This is a different word. A phonon is the word for an excitation within a crystalline structure. So you have some kind of crystal lattice. Obviously, the cube was the easiest thing to draw, but you can have very complex solids that have very interesting, intricate crystalline structures. And the idea is that you have one atom in one corner is vibrated, and that causes a harmonic vibration in the entire structure. You can look for this. And another technique is to look for a boiling in a superheated liquid. So if you've ever tried to boil water in the microwave, and if you do it with very, very clean water in a very clean and smooth container, what can happen is that the temperature of the water can go above the boiling point, but the water still doesn't boil. And this is called superheating. And a disturbance will trigger boiling. That disturbance can even be a microscopic one from just one atom being hit with the right amount of energy. So these last two, the phonons and the superheated boiling, can sort of be locked together under the umbrella term of heat or motion of atoms. So more traditionally, you might see this as a triangle between light, charge, and heat, although there are other possibilities besides these. These are sort of the basic ones for different technologies you can use. But I'm not going to go through all of them. Of course, I don't have the time tonight, so I'm going to focus on the technology that I work on. And that combines the top two, combines light and charge. So many robust dark matter experiments will combine two of these detection channels because that gives you more information on background rejection, energy and position reconstruction, things like that. It's always good to have more information. So this is a video that illustrates how the lux or any similar detector to lux, how they work. I'm currently working on the successor, the next version of lux called LZ, but this is a great cartoon that illustrates, this video will illustrate the fundamental principle for you. So the material that I use in my work is liquid xenon. And the reason why we use liquid xenon, there are many actually, it has a lot of benefits. So xenon produces light and charge when radiation interacts with it. So that's great. We can use it to look for dark matter by collecting the light and the charge that come from an interaction. It's also quite dense. So when xenon is liquefied, it's about 3 times denser than water. And so since we don't know what dark matter is, except that it seems to interact very rarely, you want more atoms. And so dense is good, so you can have a multi-ton scale compact detector in a small space. And it's not even that cold, so xenon liquefies at a temperature higher than liquid nitrogen, so it's convenient. Xenon is naturally around in our atmosphere at a very small percentage, so that's where we get it from. And xenon's used in other things. It's used medically, it's used in lamps and lights, so it has a lot of different uses. So we have this big vat of xenon. So lux was 300 kilograms, which is about that big, and then the next generation LZ is going to be 10 tons of liquid xenon. So you have this vat of liquid xenon, and what happens is that you have metal grids, an anode and a cathode. So you're basically creating a giant battery. You're creating an electric field, and it'll become evident soon why you need that electric field. These blue squares at the top and bottom, these are sensors that pick up light. So here's our dark matter coming in, the little blue ball like a WIMP. It hits a xenon atom, we get a flash of light from excited electrons, and that's our first primary flash of light. But we also had some electrons that were liberated, that were ionized from their parent xenon atoms, and see now you have this electric field. They get dragged up to the top, and at the top, there's a bit of gas xenon that sits on top of the liquid xenon, and that creates a second pulse of light. So the time in between the liquid and the gas pulse, that tells you how deep the event was. And the hit pattern of light on these photon sensors, the hit pattern tells you where the event was in the other two dimensions, in X and Y radially. So a device like this allows you to reconstruct position in 3 dimensions. And the reason that's important is because there's no reason why dark matter would only interact with the edges. But if you're ordinary radiation, like a gamma or a neutron, you're going to preferentially interact in the outer edges because xenon is dense and it's a massive atom, and so xenon is going to stop and catch most types of radiation will be in the outer edges. And so the reason why you need 3D position reconstruction is because when you're looking for dark matter, you want something that is randomly anywhere in your detector. So you focus on your analysis towards the center of an experiment like this. So you have 3D position reconstruction, and the amount of light that's produced and the amount of charge that's dragged up and then produces a second pulse of light. So everything is light. The secondary interaction that gives you the charge is then converted into light. So what you're doing is looking at 2 flashes of light. And these flashes of light, the brighter they are, it tells you about the energy that got deposited. So you know where it happened and how much energy went into the interaction. So that's what makes this a good technology. You get this great information. So that's just a video. Here is a picture of the actual lux, well, not the innards of it, but this is the titanium cryostat that housed lux. And cryostat is just a fancy way of saying a thermos. It's a giant thermos. It's a giant titanium thermos. It's got to be a thermos because we got to keep the xenon liquid, right? That happens at cold temperatures. So it's not as quite as cold as liquid nitrogen, but we do use liquid nitrogen to help liquefy the xenon, keep it cold. But it's a double-walled vacuum jacket container. And the reason why it's made of titanium is because the great thing about titanium is it's strong, but it's not as dense as steel. And so it makes the whole thing more lightweight. And we were also, for Lux, able to find special, like really chemically pure titanium, very low in the bad contaminants, things like uranium that produce radiation, everything. Every metal and plastic you buy has uranium, thorium, radon inside of it. And it's fine for us, the radiation is not harmful at these tiny levels to humans. But when we're trying to make a discovery, every extra bit of radiation is bad. So this is special titanium. It's not off-the-shelf titanium, but it's extra purified to remove impurities, including the radioactive contaminants. So this is a very low radiation titanium. And this is a picture of myself here and one of my former postdoctoral scholars. Before that, he was a PhD graduate student. This is Jeremy Mock in the green hat. And this is one of the last pictures that was taken in front of Lux before the outer detector was filled. So Lux sits at the center of a water tank because even though we're deep underground, and even though we built this out of special titanium and other great material, you still have radioactivity in the rock, the cavern walls, naturally occurring. I'm not talking about unusually high levels of radiation. I'm talking about natural, normal amounts are still too high for an experiment like this. So what the water does is it shields the radiation. So you may think that, wait, why water? Why not something like lead, right? So the thing about water is it's great at stopping neutrons, and remember that neutrons, as far as we know, look identical to dark matter, so that's very bad. So the water shield not only shields us from radioactivity, from the naturally occurring radiation in the walls of the rock of the mine, but also it allows us to catch those few lucky cosmic rays. So even though we're a mile underground, you still occasionally get a lucky, very, very, very high energy cosmic ray that can penetrate through a mile of rock. And you don't want to mistake that for dark matter, right? And so another purpose of the water tank is particles will come in and interact in the water. And so if something interacts in the water, and in a very small amount of time, there's this interaction inside a flux, we know, oh, that can't be dark matter. Because dark matter, it interacts so rarely, you're never going to get it scattered multiple times, even in different materials. If it did that, we would have discovered it in the 80s already. So we know that the probability of interaction is very small. And so we can just like we use multiple scattering for neutrons inside the liquid xenon, we can do what's called a coincidence timing. If two things are, relatively speaking, simultaneous in the water tank and inside the xenon, that means, oh, that was not dark matter. So we build a very careful experiment. But this is very far from being the only one. I told you how there's all these different technologies. So I'll probably get, so if you speak ill about any competitors, I'm sure I'll get, if this ends up, my talk will hopefully be on YouTube, I'll get some angry comments from some of the competitors, but, they're not here right now. But basically, right now, the leading technology is based on liquid xenon. Here's an inside picture, you saw the outside. Here's the inside of Lux, and its successor, LZ, will look very similar. You have copper plates that hold the sensors that read the light. I should emphasize these sensors that go in these holes here. This is much more advanced than something like the cameras that we use in our daily lives. These are called photomultiplier tubes, or PMTs for short. They're sensitive to single photons, individual particles of light. I'm pretty sure even a cat or a frog's eye cannot do that. So in fact, if you turn these on in what you would think is a dark room, you might break them. Like literally, they'll break and start smoking because they're powered by high voltage. So they can be blinded by too much light. Like the lighting in this room would instantly destroy one. So these are very sensitive pieces of equipment that look for very, very tiny flashes of light. And specifically, I don't mean visible light, but liquid xenon scintillates in the ultraviolet. It turns out, who would have guessed? It's very convenient. Teflon is a mirror for ultraviolet. I don't know why. I don't think anyone does, but that's convenient. So we make the walls out of Teflon. So that bounces the ultraviolet light into one of our sensors. There's also, so this is the xenon experiment. They stole the name of the element and just capitalized it. So the xenon experiment, which is deployed in Europe, at Gran Sasso in Italy, it does have also a substantial fraction of American collaborators, is competing as is Panda X, the Panda X experiment in China. These are essentially identical experiments. Each of them will tell you, well, not identical because theirs is better or the best, but these are essentially the same experiment over and over again because of the immense advantages that I was telling you about liquid xenon. Does that mean liquid xenon is perfect? It's the one magic material to look for dark matter? Certainly not. Many people have different ideas using liquid argon, neon, the argon one, germanium, silicon, other kinds of crystals that produce light that scintillate, bubble chambers using the superheated liquid idea I mentioned earlier. And what you're seeing here is only a small fraction of the worldwide dark matter effort. Everyone wants that Nobel Prize. So this world map is outdated, but it is illustrative of the extent of this effort. And so these are different underground locations, like mines, for example, where we have enough rock above us, or mountains, not always underground, but sometimes like Gran Sasso in Italy, you can actually drive into the quote-unquote underground lab, because it's not really underground, but it's under a mountain. That's good enough. So that's adequate. You need stuff above you to block cosmic rays. And so this is a worldwide effort, but in the US, there really isn't a lot of spare cash anymore for fundamental research. So there was kind of what was called the down select, where only a couple experiments were chosen. And the US Department of Energy, actually, in terms of WIMPs, there's also other kinds of dark matter, like axioms, and there are 2 WIMP experiments that were selected, and that was LZ, which is Lux Successor and Supersede EMS. Now, if anyone knows Hunger Games, they'll know why I picked Katniss as LZ and Pete as Supersede EMS. So there's Supersede EMS people watching this, they'll be very angry. But hey, you won too. You may not be Katniss, but okay. So there was sort of like a very, again, my colleagues will be really mad that I'm saying this. There's a very backstabby sort of thing that happened because, again, there's not enough money for fundamental research, right? We'd rather build missiles and other things. So there's not enough money, so we have to select, so the Department of Energy had to decide what are the best dark matter experiments that can be selected to move forward. And LZ was chosen. LZ is a successor to LUX. It stands for Lux Zeppelin. We combined with many other international collaborators, from UK, Portugal, Russia, to build, and South Korea. And so LZ, it stands for two of the predecessor experiments of it. And it's going to be a bigger, better version, essentially, of Lux and Zeppelin, its predecessors, where you have a larger amount of xenon, and it's going to use the same water tank that was used for Lux. And Supersede EMS is one of the germanium crystal-based experiments, so it's a very different technology. It's not looking for flashes of light, but for something to come and shake the crystal lattice. So what do the results look like? What have we found so far? The answer is we have found nothing. So despite all the massive amount of cosmological, astronomical evidence for dark matter, we have not found it. Instead, we've been measuring zero with very increasing precision, essentially. So what this cartoon illustrates for you, what do the results of a dark matter experiment look like? So when you find nothing, what you do is you put a curve on a chart like this. So here you see an orange experiment A, experiment B, experiment C. And what these curves mean is they're statistical statements that you're confident that dark matter isn't that way. And so anything above a curve is ruled out. So on the y-axis, this is the probability that dark matter is going to interact with ordinary matter. And so we keep going lower and lower and lower and lower and lower in probability. We also don't know what's the mass of one dark matter particle. So this scale is the mass. And now the reason why these curves are shaped the way they are is that if dark matter has too low of a mass, then it's like a ping pong ball. You're trying to detect a ping pong ball with a billiard ball. That's not going to work. So the energy that dark matter gives one of your atoms in your experiment is not good enough. You can't see it. You can't see the light or the charge or whatever it makes. So that's why it's very hard to do experiments down here. Now the reason why the curves all curve up here is because we're pretty sure we know what the density of dark matter is locally in the Milky Way galaxy. But if you don't know what the mass is of one dark matter particle, that means if it's super heavy, then one dark matter particle, is good enough, right? One here in this room and one out by Neptune's orbit, and suddenly on average you get the right density. And so if dark matter is really heavy, then our experiments won't be sensitive because there's not a great enough number density of them around. So that's why these are shaped like this. It's easiest to look for dark matter at sort of Goldilocks medium masses. That doesn't mean it's here. It could be here or here, in which case that means we have to be more clever about the experiments we use to look for it. So there have been claims of signal over the years. I'm not wasting time on them. I talk because there's been no conclusive evidence. They always get ruled out or explained by something else. There's been one persistent claim of discovery by the Dama Libra experiment in Italy, but pretty much no one believes it anymore because it's been checked so many different ways, and now we're checking it with the exact same technology to be extra sure. But it's pretty sure, most people are pretty sure that it's just some sort of misunderstanding of the detector behavior. And so there is no conclusive discovery right now today. But we do have these blobs in plots like this that come from models like supersymmetry. So this is just a cartoon. But here's a real version of a plot like this. So this is from the LZ, the Love Zeppelin collaboration, and this one I may have a slightly outdated version. And dark matter were just these swishes that you saw illustrated on the previous slide. These swishes just keep getting lower and lower and lower. It's like Ed Brown Poe, right, with in the pendulum, and the pendulum keeps swinging lower and lower and lower. And we're not finding anything. And we're killing these beautiful models. And the theorists always get so mad, you killed my beautiful model. Well, it doesn't explain reality, so tough. So we keep all these gray blobs you see. These are predictions of where we should find dark matter. We keep blowing past all the predictions and finding nothing. Eventually, we hit what's called the neutrino floor. And that's bad. So in orange, this represents what's called the neutrino floor. This is where neutrinos become a problem. So I don't have time, you can ask questions, of course, to go into what's a neutrino particle, what's that, but it's a particle we already know was discovered in the 1950s, and it interacts very rarely, just like we think dark matter does. The problem with neutrinos is that if you build a big enough detector to look for dark matter, you've accidentally built a great neutrino detector, which is fun if you want to do neutrino physics. One individual's back signal is another individual's background. So what one scientist thinks is great, the other one thinks, no, that's the garbage we have to throw out. So if you're looking for dark matter, neutrinos, yes, they're interesting, and you could learn all kinds of things like solar neutrinos teach us about the inside of the sun, so that's exciting. But if you build a big enough detector, all you're going to see is neutrinos, and you keep triggering on neutrinos. And so eventually, we're going to hit this neutrino floor. There are clever ideas on how to work around it, but it's still the case that probably in a couple decades we may, unless we have, really clever new ideas, it may be difficult to continue the search. So hopefully dark matter is not that low. So the numbers, to give you an appreciation of the numbers here, we've gone down to 10 to the minus 48 square centimeters. So we measure probability in terms of surface area. That's a long story why, but I think the easiest explanation is think of a dartboard and darts. And so we're measuring the probability of a dark matter particle hitting one of the nuclei inside one of the atoms in our detectors. So we measure probability in units of surface area. So this is 1 square centimeter. We're down to 10 to the minus 48. That's 0.0000. That's 47 zeros. So that's a really small number. Most calculators you put that into will just say 0. It's rounded. So, and that's only here. As I explained earlier, we're doing more poorly at low masses because not enough energy is being imparted. But this is the current picture. Now, to paraphrase President John F. Kennedy, who was talking about going to the moon and why we go to the moon in his famous speech in the early 60s at Rice. And I'm going to sort of change the word slightly and say, do my best Kennedy impression, though. We search for dark matter, not because it is easy, but because it is hard. So that's if you replace dark matter with blue, that's exactly what it says. So this is not easy. This is not an easy task, but the technology has been improving very rapidly. So you may be familiar with something from computer science called Moore's Law, that you can fit more transistors, like twice as many every year or two or something like that. I forget the exact numbers. And it seems to keep working because our technology improves, and when one technology peters out, another one takes over, and Moore's Law continues. We've been able to keep that going in dark matter, where first we had the germanium and sodium iodide, these crystal-based technologies were really leading the charge in the 1990s. And then we've got liquid xenon in the 2000s, and then we have with discrimination, which means the ability to tell the difference between different types of interactions. That's very powerful. We get down to Lux, which we just finished, and xenon 1 ton is now running, and it's switching to xenon n ton. And then we have LZ, which is going to be competing, which is Lux's successor, and is competing with xenon n ton is going out here. You see this is starting to flatten out. That's not because we've hit the neutrino floor yet. it's because we have other problems. We've got radon, we've got other background noise that's preventing this from being a straight line again down here. But we have been doing amazingly well. We keep finding nothing, but doing it with incredible precision. So, now, I'm a huge fan of Star Trek, as you know. I started with Lieutenant Commander Data when I tied him in with Asimov and the Positronic Brain. So dark matter is always showing up in science fiction. It shows up a lot in Star Trek, completely inaccurately. So dark matter is not going to be a blue nebula that you can actually see. It's not going to make you fall through the floor. That happened in the Star Trek Next Generation, and more recently Star Trek Discovery. You're not going to have little purple pills made of dark matter that kill you. You know that's ridiculous. So, but I will. It's still fun. So I'm going to start wrapping up, and I will be very happy, of course, to answer any and all of your questions. So, in conclusion, in the end here, I came up with, I showed you all this evidence of dark matter, yet we still haven't found it. So, but I want to emphasize that sometimes non-discovery is just as important as discovery. So, unfortunately, I can't tell that. I tell this. So, colleagues in other fields are always shocked when I tell them, I'm publishing no results. They're like, we're not allowed to publish no results in my field. I'm like, my entire career is based on publications of no results. It's called the scientific method. Look it up in your 5th grade textbook. They get very mad, of course, when they say that. But in psychology and other fields, they're like, oh, you can't publish a null result. But if you look at physics, if you look at the history of science, it's incredibly important. One example of this is the famous Michelson-Morley experiment from the 1890s, early 1900s, where they failed to see the speed of light change, because they accidentally discovered the speed of light is constant, as Einstein postulated special relativity. So that was one of the first pieces of evidence of special relativity, that the speed of light is constant. So it could be that we may need to adjust our thinking. If dark matter is a particle, maybe it's in one of the regions where we haven't been able to do so well, and we need to shift our technology. Maybe we're not entirely on the wrong track. We may be on the partial right track, and maybe need slight adjustments. So we're doing a lot of thinking in the field about this, of course. So we still know, despite the lack of discovery, why are we so certain dark matter is there? It's because of all the evidence I showed you from astronomy and cosmology. So what I do is more you would call particle physics. But the astronomers and cosmologists, astrophysicists have given us a mountain of evidence that there's something funny going on out there. And so that's why we're still pounding away. Why are we still so sure? It's because we have all this evidence. And if you look in other areas of science, all you need to do is look at the recent discovery of gravitational waves to see sometimes it takes decades of patience. If you look at the story of gravitational waves, that goes many decades back. And so it could be that just like with gravitational waves, we just haven't built a big enough experiment yet, so we keep building them bigger. Or, as I mentioned, we might not just need to build bigger, we might also need to build smarter and slightly change tactics. We're pretty sure dark matter is there, and we have a fairly agnostic way of directly looking for at least one generic candidate to win. And so that's through the method of direct detection, through flashes of light or charge. There are 3 major ways to find it, using indirect or direct detection or direct production. Tonight, we focused on direct detection, where you look for a nucleus inside of an atom to basically get punched with one of these dark matter with particles enough energy to produce something that you can measure. Light, charge, heat, some sort of chain reaction of a few more atoms are hit after the initial interaction. And so the hope is that dark matter doesn't just couple gravitationally, but it has some other coupling, some other interaction with protons or neutrons that we can capitalize on. So experiments like LUX, its successor, we'll see in competitors, Xenon, 1-ton, N-ton, and Panda X, are really putting the squeeze on various models and ruling out large amounts of the potential theoretical parameter space where dark matter could be. So this is an actual picture of my car. My license plate really is Xenon. My LUX collaborators were very upset. I thought they would love it. I shared, like, oh look, I got a xenon license plate. And they're like, have you joined the xenon experiment? They're a major competitor. And I'm like, it's not my fault that the xenon experiment stole the name of the element and then made it capital, not even an acronym. I'm like, no, this is for the element xenon, not the experiment. Although, living in New York State, I'm absolutely shocked that this is not taken already, because the spokesperson of the leader of the xenon collaboration is Professor Elena Aprile at Columbia University. Why doesn't she have this on her card? So I've been tempted to drive up to Columbia in Manhattan and just like find, where she is, her building office, and just like park my car. Of course, because it's Manhattan, you can't park anywhere, but I would love to do that and be able and just like show off that I stole the idea from getting it from my car. Then again, if she lives in Manhattan, maybe she doesn't even have a car. That explains it. Yeah, maybe she doesn't even have a car. So I do hope. I do more than just hope. We're planning all contingencies. We have exploring different technologies, but hopefully we are looking for dark matter in all the right places and not missing it. And so with that, I'll conclude. Thank you for your time, and I'll be very happy to answer your questions. Thank you. Yes.
I've just a comment. You're in good company with your license plate, because Murray Delmon, the Santa Fe Institute, has quark.
I have not seen quark, but I've seen top quark. I parked next to top quark once at a conference. I think I saw a hand up here.
I've seen Murray's car in New Mexico.
Is the dark matter more dense towards the center of the galaxy, or is it denser around the galaxy, or is it all the same?
This is a great question. Because it interacts with gravity, we think it should be denser at places like the center of the galaxy. So one of the ways we've been looking for dark matter, it's different than what I do. I do direct detection. But I had mentioned indirect detection. One of the ways you look for dark matter indirectly is look for extra radiation, extra particles coming from centers of galaxies. So there you're not going to detect the dark matter from that distance directly, but you try to look for byproducts of dark matter interacting at these places where it should be higher density.
So if it's higher density towards the center of the galaxy, why is it causing the outer edges of the galaxy to spin faster?
So that's because since the gravitational field, just like from the sun, it still has an infinite reach. And you still have some density, even though it's a smaller density, you still have a very significant density even out to the outer edges of the galaxy, enough to change the speed to explain what we observe. So yeah, it does seem a little weird, but it works out mathematically, where there's definitely a drop-off in density as you get away from the center of the galaxy, but still enough left in order to explain the revolution at the outer edges. Yes?
Interesting thought. With there being more matter than there is antimatter out there, is there any correlation between that and the matter, atomic matter mass versus the dark matter?
We have no idea. That's a great question. So it's one of the great cosmic mysteries, actually. Why would we exist at all? Right? Why isn't the universe just full of energy? Why, after the Big Bang, weren't there just equal amounts of matter and antimatter? We don't know. But for some reason, a few seconds after, or fractions of a second or so after the Big Bang, somehow there was an imbalance between matter and antimatter. But a very significant one, not significant, actually, other way around. It's very insignificant. Something like one extra particle of matter per a billion of antimatter, something like that. That explains why we exist, why antimatter all disappeared and there's matter left. We're not sure if that's tied to dark matter. The numbers are very different. When it comes to dark matter, it's about 5 to 1. With dark matter, it's 25 to 5%. And so we're not sure, are those numbers, are those ratios related? We don't fundamentally understand the asymmetry between matter and antimatter, so we're not sure, is that related also to the imbalance between dark matter and matter, which is a much smaller difference. Any other questions? Yes?
What are they doing at the South Pole?
So there are many different experiments going on in South Pole. The one that's most connected to dark matter is the ice cube experiment. In the ice cube experiment, what they're doing is actually they're using the Antarctic ice sheet as a radiation detector, just like the water tank is in Lux. It's a lot of frozen water. And so what they're doing is they're looking for particles that don't interact very often, like neutrinos, that can go through the entire planet Earth and go through the Antarctic ice sheet. So ice cube is essentially a neutrino telescope that looks at neutrinos passing through the Earth. Now the connection with dark matter is maybe neutrino particles are a byproduct of dark matter, just like the indirect detection I mentioned earlier. So they're looking for evidence that there's some mysterious additional neutrinos that can't be explained, and maybe those neutrinos are byproducts of some sort of dark matter interaction. So their primary goal is not dark matter, it's studying very high energy cosmic neutrinos, but there may be a correlation, there may be a connection there. Any other questions, Ron?
Yeah. Interestingly enough, the Voyager 2 spacecraft just broke through, quote unquote, the heliosphere, okay? Does this have any possible significance, because they are tracking it, they're receiving the signals, whatnot, that as it gets into away from solar wind and other particles now, it's in a region of just barely maybe just touching the edges of interstellar space, that there's something there, some factor from dark matter, something that may or may not have a possible effect on the craft itself.
Well, it's not the first spacecraft to do that. I think Voyager 1 did that a few years ago,
Right.
and we didn't see anything weird. But yeah, I don't think, unless there's a local overdensity of dark matter, I don't think it's on such small scales. I don't think there's enough for an interesting effect. So the thing about so this is exciting, these are the furthest human-made objects, but unfortunately the flip side is in the grand scheme of things, it hasn't gone anywhere when you look at the size of our galaxy. So in the grand scheme of things, those craft have if I zoomed out, they're like laughably not, on a reasonable map it would still be, you put it at the same dot where you put the sun and the earth. Is the scale of how, and even though these craft have traveled such a mind-boggling distance for us, that distance is nothing compared to galactic distances. So unless there's a local clump of dark matter, which is possible, some extra clump, then it's not, you don't have enough dark matter locally, I wouldn't think, to have some sort of interesting, different gravitational effect, not that I'm aware of. Any other questions?
Hi, I'm Ron Barnell, the president of the Hilbert Sky Observatory, and wasn't that just great? I mean, really. I apologize for not being able to be here earlier, but, I was gonna say a few words, show these on our project out here to put, the region's dark sky observatory. We're working out here in Rensselaerville and trying to obtain some property and get some interaction between the Height Reserve out here and the Carey Institute. And if you follow us along on our Friends of the Hilbert Observatory Facebook page, I think you'll be hopefully surprised at some interesting developments that will be coming up in the new year. So again, I'd like to thank Dr. Szydagis for just incredible, engrossing. It's so great to be alive at this time and just see what's going on in the field from what us astronomers have seen the development, just exponential growth in knowledge, just incredible. We're going to have a reception here following up at the restaurant. Just go up the hill. Please do join us, and we'll have a hopefully good social interaction. Ask Dr. Szydagis more questions and some more insight. So Thank you all for coming, very much appreciated, okay? Take care.